Hi everybody. So in this video I want to define electronegativity. So this is a diagram from the mineralogy textbook by Klein and Dutro, and it's a very nice diagram. What it shows is this three-dimensional view of the periodic chart where the height of each of these boxes represents a quantitative assessment of electronegativity. We'll look at the quantitative aspects of electronegativity a little bit later, but I just wanted to show you here how electronegativity varies across the periodic chart. So first, let's start with the definition. What is it? So qualitatively, electronegativity is essentially it's a measure of the ability of an atom to attract an electron to itself. So ability of an atom to attract an electron. And let's use E minus as an abbreviation for an electron. And then to itself. So it's going to grab an electron, and not from anywhere. It's going to grab an electron from another neighboring atom. So if you look at, let's say, lithium or sodium. Let's take lithium in this case. So you'll remember from our prior lectures, our prior videos on the periodic chart, lithium is here in the second column, and we're filling in the s orbital, and so it's got this 2s1 electron. So it's got this lone electron in its outermost orbital, and if it dumps it off, then it will achieve a noble gas state. It doesn't want to bring electrons in. For lithium, which is this guy here, it's going to have to add 7 more electrons to get all the way out over here to the end of the periodic chart where it would have a filled outer shell. It doesn't have enough protons. It's only got 3 protons. That's not enough positive charge for it to bring in 7 more electrons and get to the 2s2, 2p6 electron configuration. So instead of trying to bring in 7 more electrons, what it's going to do is just try to get rid of that 1. So lithium is most likely going to be in the 1 plus charge when we find it in nature. So what does that mean for electronegativity? It's got a very low electronegativity. It doesn't want to bring in electrons, it wants to get rid of them. If you take a look at oxygen over here though, it's got a very high value. You can read the value here. It's got a value of 3.5, which is relatively high. So oxygen, it typically has a 2 minus charge. And the reason for that is because in its second shell, it's got a filled, well, let's write this a little bit better. It's a lowercase. Get rid of that. It's got a 2s2 and a 2p4. And if it can only bring in 2 electrons, then it'll have a filled outer shell and become a 2p6. And then it'll have a noble gas state. What's its other option to achieve a noble gas state? It can get rid of all 6 of these electrons, and then it would have a filled outer shell of 1s2. But it has 8 protons, and so with 8 protons pulling in those electrons, it doesn't want to give up 6 electrons. So an easier path is for oxygen to be able to pick up 2 electrons and add them so the 2p4 becomes filled, and we get a 2p6. So that means oxygen has very high electronegativity. Fluorine is higher still. Fluorine has an electronegativity in this chart of 4.1. And that's because fluorine has an outermost 2p5. Forget about the s orbitals. We don't care about those for now. All it needs is 1 measly electron, and it achieves a noble gas state. So it's very happy to bring an electron in. So in general, as we go from left to right across the periodic table, we see electronegativities gradually increasing, being very high over here on the right, because these elements are just, these in the last column are just 1 step away from achieving a noble gas state if they can bring in an electron. And these guys over here have very low electronegativities because all they have to do is get rid of 1 electron. They don't want to bring 1 in, whether it's sodium, potassium, rubidium, cesium, francium. They want to get rid of an electron, not attract one. So they have low electronegativities. And that affects the nature of the bonding. As we'll show in a different video, when the electronegativities are very different from one another, we get strongly ionic bonds. When we get things that are very similar in electronegativity, the bonds tend to be more covalent. They're sharing rather than transferring electrons.